Good morning and a warm welcome to our second session today. We started the day with a great presentation and are looking forward for our next session. My name is Doreen Schäfer and I will moderate this webinar. Next to me is Timur Uludag. Welcome.
Thank you, Doreen.
He is a product manager from our product area Magic Power Division, and he will present to you today Overvoltage protection for safe operation, transient protection for non-isolated DC-DC power modules. Voltage spikes can cause downtime and damage, but how do input filters help protect 24-volt bus systems? Let's explore the solution. The stage is yours.
Thank you. So, a very, very long name. Overvoltage protection for safe operation, transient protection for non-isolated DC-DC power modules. So, we will cut it down now and dig a little bit deeper in how we can get around this. First of all, this word transient. Let us explore what are transients. What we see here is somehow the try of an explanation, a little bit more technical. That means transient overvoltages can be defined as a short-term deviation, means a variation, from a nominal voltage value, which exceeds the permissible tolerance range of the nominal voltage in the electrical system. Means if I have got 24 volts and the voltage goes up more than 24 volt, then if there is a defined range for the 24 volt and I exceed this range limit, then we call it a transient. Second, what are the effects of transients? The effects of transient overvoltages are mostly destructive. Means that the input stage can be damaged or the whole bus could be damaged if the transient is not suppressed and it proceeds in the whole system. For the next steps, we will base all our evaluation, the discussion, on a typical electrical system as you can find it in the industry. Here, you can see the basic structure of an industry plant. We have got here the separation of the source where the voltage goes in. Here you have got then the generation of the 24 volt. Then here on the right side, you have got all the stuff that is going to be supplied, and the whole supply will be done through this connection lines, through this distribution lines, this DC bus here. From where can transients come from? Mainly, we have here two. Here, A means if we have here a lightning strike and that goes through the whole system and damage then here all the other parts, or something that is internally generated, like here if I have got a motor drive and it goes from full load to zero load, and then the voltage at the input shoots over, and this over voltage, this transient, is going to be on the whole bus system here. For the further discussion, we will concentrate here on the connection lines here. Means here we assume that the 24 volts were supplied. It goes here then to the device that's going to be supplied, and then here to the DC-DC one. Let me make a short interrupt. What we are now telling here, like the lightning strike or the internally generated, these are, let's say, the ones that are well known. All the other ones could also be possible, like that we have got two cables that lie in parallel, and we have got a capacity coupling, and it comes, let's say, from a frequency converter. This could also be a possible internally generated source, but we will focus now on what I have shown here. So, to protect the DC-DC power module from transients, we need something in between where the voltage comes from and where the voltage is needed. This is here the area we are playing today. This is then the EMC filter concept that is shown here in red. The EMC filter concept for a DC-DC power module is normally divided in two blocks. We have got here the green one. This is the immunity filter. This is part, or this is the main discussion point today. And we have got here the emission filter. The immunity filter concept is based here on a two-stage concept. One stage, here, the first stage, to clamp the high transient voltage during a surge event, which can be achieved by a unidirectional TVS diode. For the second stage, here, a passive LC filter is recommended, which attenuates the voltages that exceeds the maximum operating voltage of the DC-DC power module. The emission filter concept is based on an LC filter. The values for the LC filter can be looked up at the power module datasheet. As a guidance, how to estimate LC filter for different operation points for the power module, you can check here the highlighted app note I wrote, how to get it done for other operation points. We will check now which parameters we need to design an appropriate immunity filter. The shown 5 parameters are often referred in several lectures, books, and other webinars for selecting an appropriate TVS diode. It goes, or it starts with the supply voltage for the device that's going to be tested, the breakdown voltage we have got here, the maximum peak current, the power dissipation, and the maximum clamping voltage, where the diode carries the peak current. For the next steps, we will focus on the major 3 points we need to design an appropriate filter. A consideration of I peak and P dis, the dissipation, the losses, would go beyond the scope of this webinar, because special for the losses that generates heat, there is a lot of knowledge about first the product and then also how to solder it, how many PCB space we need and other steps needed. But for now, only the 3 steps. For our power module, to have here somehow a real-world example, we take our SIP3 power module, where you have got an input voltage from 8 to 36 volts, so a very good one for the 24-volt bus, and we go out with a V out of 5 volts. So, first, let's start with determination of VDC. The maximum occurring DC voltage is decisive for the interference immunity of VDC, not the nominal voltage. With a 24-volt bus, the voltage range of 19.2 to 30 volts is specified in industrial environments. That means, consequently, the maximum value for VDC is not 24 volt, it is 30 volts, because this is the highest value that is allowed. Second, how to select the appropriate TVS diode. Here we take the one from our online catalog. We have got here this one, where you can see we have got a VDC of 30 volts. We have got the breakdown voltage and all the other parameters here also included. So for this example calculation, this is a pretty good one. Where can I find the breakdown voltage? First, the breakdown voltage is defined where 1 milliamp of current is flowing through the TVS diode. This value here is 35.5 volts. It is not a really fixed value. As you can see here, you have got here tolerances plus minus 5%. This is because we're talking here about a PN transition. Therefore, we have got then a range of 33.3.5 volts to 36.8025 volts. To ensure effective protection, the VBR of the TVS diode must be higher than the maximum normal operating voltage of the circuit. Otherwise, the diode would already respond, means it would already start to clamp during normal operation, what is not the intention. Next, the value of V-clamp can be found in the datasheet as well. For the chosen diode, the voltage is 48.4 volts based on a peak current of 31 amps. So far, this value assumed or is based on the laboratory equipment. That means we have got here a base of 25 volts. However, the reality, as everybody knows, in industrial plants, where you have got a lot of heat sources, a lot of other supplies, is different. For now, we choose as a real world application example, we choose 55 degrees. Therefore, the value of V-clamp needs to be modified. But how can we do this? Here there is an equation where you can see that we need the 25 volts value of V-clamp, means this 48.5 volts, and then we have to multiply it by a temperature coefficient, and here also the factor we have for the delta between 25 and 55 volts degree. If you all mix it together, then you can get to this equation, means at 55 volts we are nearly 50 degrees, means we are at about 49.84 volts. If you check out this here, this is the 25 volts degrees value. There is a pretty difference between these two voltages, means the temperature has here a very big impact on the clamping voltage, means at the voltage where the maximum clamping is done. This value will be now the starting point for dimensioning our second stage, means the LC filter. So, to make a short break, the TVS diode is done. Here we know how many voltage we have. We know what product we can use here. So we have got here this green tick. The next is the LC filter we have to design. How can we now get to the value that we need so that the voltage that is going to be fed in the LC filter is damped to a value so that the power module that is here is not going to be damaged. This we can go here with the small equation everybody knows. Then, if we put in the values that we need, the value for the VPM max can be found in the absolute maximum ratings of the datasheet of the power module. And this VPM max is an absolute maximum input voltage, which, if you exceed it, will result in a permanent damage of the power module. That means 44 volts is the absolute max, means you cannot go further. If you go further, something bad will happen then. With the VPM max value and the value for the VClamp max we have from our previous example calculation, we can see that we need at around minus 1.08 dB. Means we have to design now an LC filter that makes a damping of nearly 1 dB between the input and the output. To calculate the values of the needed components, we take here now the shown simplified circuit diagram. Here the TVS diode is represented by a simple voltage source. The power module circuit is separated by the input capacitor, Cin, here. Every power module needs an input capacitor here, and the input resistance of the power module. Means if we take the same equation we have from the previous slide, means we have to go for V noise to VCL, means here V noise, VCL. If we then put in all the values we have got for LFI, CFI and all the other ones, then we get to this equation here. But this equation shows not all the parts we have in reality. With the already existing emission filter of the power module, the circuit can now be redrawn as shown. As you can see here, we squeezed in the emission filter. For the calculation of CFI, we have to choose corresponding filter inductor as a start value. As you can see, if I, let's say we want to have this CFI, then there are too many variables in there. That means we start with the value of LFI and make it as a starting point. As LFI is in series with the application and therefore its RDC causes unwanted losses, the inductor with the smallest possible RDC has to be chosen. So that we will get up here with something at about 12 microhenry. And if we then take here the RPM, the value of the input resistance of the power module with 101 ohms, we got here 1 kilohertz as the frequency. The frequency is based on a surge impulse. We have got here this 2 times 4.7 microfarads. We have as the input capacitors for the power module, and CFE means we have got here the capacitor for the emission filter. Then we will come up with something at about 280 microfarads. This here is now an approach that we say, if you go and calculate all this, then this is okay, but if you want to select something, then you have to have also the freedom to play with the parts. Means what you can see here is the value of the inductor and the filter capacitor that comes up, that is put in, means all the points here on this curve represent a combination. You can choose to get to the right attenuation you need with this combination. Means if you would somehow decrease the inductor here and go up this curve in this direction, let's say 5 microhenry, then you have to go up at about 600 microfarads. If you would, on the other hand, go in the other direction, mean you want to increase your inductor because you have better inductors with a higher microhenry value. Let's say you go up to 20 microhenries, then you can see that you would need, let's say, something about 110 microfarads as a filter capacitor. So it's always the combination of C and L you have to look. This is for the first calculation we did the slide before. We choose an inductor value of 12 microhenry because of the RDC value and the current capability. Here we had this WE-PD2 series in mind. Let's summarize now a little bit the values we have achieved, we have calculated. As you can see, with the equation we have shown, if we would stick to 25 degrees value and a clamping voltage max from 48.4 volts, depending on the data sheet, would take then our 12 microhenry inductor, we would lead up to a filter capacitor, our CFI, of 178 microfarads. If we then be clever and take the real world temperature, 55 degrees, which would lead to a different V-clamp max, 49.8 volts, we will get up to 280 microfarads. That means if we have here somehow a delta of 30 degrees, this leads to a difference in the CFI value of 22%. This is significant. Means if you underestimate the effect of the temperature to the clamping behavior and therefore the maximum clamping voltage, you would probably choose the wrong capacitor. If you choose the wrong capacitor, that means you have got insufficient damping. If you have got insufficient damping, the transient will propagate in the whole system, means you will first damage the power module and then the delta that has not been clamped will also propagate in the whole system and would go further damage. Means the point you want to have, that you want to have a transient protection, is not meant then. If we summarize then here, the filter means the immunity filter with real world values. Here, what you can get, see we have got here the TVS diode, where you have got this VDC of 30 volts. We have got an I peak of 62 amps. We have got the PD2. We have got this aluminum electrolytic capacitor. Then you can see the first immunity filter here, how you can damp it, and then also here the two other values to make here the emission filter. Means this filter concept here, consisting of the immunity filter and the emission filter, is appropriate to have an EMC compliant filtering for the DC-DC power module. Normally now the first fingers will raise, yeah, but there I need two filter stages or two filters, an immunity filter and an emission filter. Yes, of course, it is possible to merge this LC filter and this LC filter to have only one LC filter that is somehow sufficient, first for the immunity protection and second to make enough damping for the emission. But if we want to go for this calculation, then this would mean this is a different webinar, because here then we also need more measurements to show how this combination could work like. So I hope you enjoyed the webinar. If you have questions, please address it. And if there are also questions we cannot answer today, then please, we have here our service and support guys. We have got our BDMs. Address them, please, and we will try to help you as quick as possible. Thank you.
Perfect. Thank you very much, Timur.
You're welcome.
That was an interesting presentation. I learned a lot about DC-DC modules.
Great.
So, first of all, before we start with our question and answer session, I will publish our your handout. Give me a second. Here it is. Okay, so all of you should be able to see the handout now, and we can move over to the questions. We had a lot of questions coming in, and I already saw that there was quite something going on. Some of them were already answered, but maybe you can just answer them again to confirm it. Mm-hmm. Let's start with a question from Herbert. From where do the transitions come from?
The transients normally come from lightning strike. This is then the point E I have explained. Means there is a bad weather and the lightning strike goes into the mains where the electricity goes into the building. A second is then it is internally generated. Means if you have got a motor that is driven and you release it, then it tends that the input voltage of the motor due to this recuperation is going to jump up, and then this more voltage propagates to the whole system. There are also other points where you can say, okay, if you have got a frequency converter that is bad connected, then if the pulses of the frequency converter are capacitively coupled to the mains connection lines, then you will have this scheme. Then you will have also all the pulses on the 24 volt, and it bounces every time up and down.
Perfect.
Welcome.
Thank you very much. Interesting question. Also, I would like to answer one question now that was already answered from Andre. Maybe you can just confirm if it's the right answer. Why do we need a second stage in addition to the TVS diode?
You need always two, because the TVS diode is temperature dependent, and as you can see, it is not possible to clamp really the full voltage then can go as a transient through the system with only one element. So the LC filter is somehow the second stage, means everything, every voltage or every transient the TVS diode was not capable to clamp will be then damped by the LC filter.
Perfect, thank you very much. So now we got your answer as well. So let's move on. There are a lot of questions in the chat. So this one is from Andre. Doesn't main transformer act as low pass and eliminates voltage peaks comes from lightning strike?
Yes.
Yes?
They should. They should, but also these LC, also these low pass filters have only, let's say, a certain region where they can work. if there is a real massive lightning strike, that means we have got here a lot of energy that is going to be fed into the system, then this is not possible. That means all the stuff that is there will be burned down, and the remaining overvoltage that this low pass filter could not damp will propagate in the whole system.
Perfect. Thank you very much.
You're welcome.
So let's hop on to the next question. It's from Samuel this time. How can we estimate the lifetime of a TVS?
Lifetime calculation is a complete different topic here. This would somehow be a second webinar or an additional enlargement of the webinar. This would go now too further. But we will note it down and we will answer him, and then we will come up with it.
Okay, so Samuel, your question will be answered afterwards via mail. Thank you very much, Timur. So let's move on to the next one. Here, we have one from Gregor. Can we use TVS diode to protect the circuit on the motor output, so from back EMF? Is it possible that TVS diode break at VBR already?
Yes, the TVS diode can break at VBR, because if VBR is not well selected, then as soon as this VBR is reached, 1 milliamp flows through the TVS diode, so it starts conducting and gets energy and also gets warm. So you should never, or you should be very, very careful to select the TVS diode so that VBR is under normal operation never going to be hit. Because if it's always hit, this VBR, then there are always unwanted losses in the system.
Wow, that's simple. Thank you very much.
Welcome.
Oh, now we have a question from Marianne regarding to our datasheets. Is SIN value of power modules available in datasheets?
Yes, the CIN value is available in all our datasheets. If you go to the section in the datasheet where you have got the design example, then you will see a circuit and a layout you should use to have the best performance. And after this circuit and the layout, there will be a section where you have got a bill of material, and there you have got explicitly named which capacitor we have used, which value, and also the part number from Würth Electronic.
That's great. I'm glad we already have it in our datasheets. Yep. So here's a question that sounds interesting. Our products are used in cold and warm climates. How do you choose our components for a wider range of temperatures?
Interesting fact. If the customer has here a special, let's say, application and temperature ranges in mind, please send it to me or send it to us, and we could help you to calculate, because if we're talking about wider range temperatures, warm and cold, could mean, are we talking now about 0 degrees as cold and 60 degrees as hot, or are we talking about minus 40 degrees up to 85 degrees, and where also at minus 40 degrees we can expect somehow a transient, then we have to calculate here different.
Well, so please feel free to reach us via email, and Timur and our experts will be happy to help you, especially with your case.
Yeah.
All right, then let's see. Oliver has also a question for you. Why do you need an emission filter before the also noisy DC-DC converter, rather than having the filter after the DC-DC converter?
Because the DC-DC converter we have here is a simple buck converter. And normally, or in general, mostly, DC-DC power modules with a buck converter have a dominant part of, let's say, differential mode, noise, And it is the best if you somehow try to get all the emissions or all the disturbances that get out of the power module and can propagate to, let's say, the 24 volt and disturbs the 24 volt with this LC filter. For those who want to have more information about LC filters, I showed it also in the webinar slides. I made an app note how to design a DC-DC power module with an LC filter. Please check it. If you have got question, address it. If you have got then at the output the LC filter, this would be then something where you have then also CISPA 32-wise different, let's say, regardings, because then you try to eliminate the interference that goes then to the load of the power module. Here with this LC filter, we focus on what is going to the supply of the power module.
Okay, got it. I hope, Oliver, it's clear for you now as well. And connecting to the thing you said about our papers, I have another question from Nadja. She asked if there are any technical papers written from the electronic regarding this topic.
Yes. So we have got the webinar I made here is also released as an application note. Means there I go more in detail, more in depth about the whole calculation, how the calculation has been set up, why we have got this equation. Due to the time frame here, this is not possible. So please check out the application note for the TVS diodes transient protections. We have got one application note out there for LC filter dimensioning for DC-DC power modules, and this is for mainly for non-isolated ones, but I have also written an application note about isolated power modules and how to get around with a Y capacitor, means a bridging capacitor between the input and the output, and how to get here a value based on the rule of thumb I have found.
Great, I see you did a lot of work.
Yeah.
And Nadja, also for your information, we will send you a link with the recording of the session and the link to the app note afterwards in the next few days. So you will be able to see the app note.
Yeah.
Yes. Okay, so we finished that one. So we have one from Mohammed. I'm not sure if you can answer it, but let's have a look at it. How to choose a TVS for wide range power supply app, meaning receiving 220 volt AC and 18 to 36 volt DC.
If you have got a 36 volts DC, I would be interested if this is the VDC, means the maximum voltage that can be on the bus. If this is the case, then you have to go for a VDC of 36 volts, and you can try to select it over our online catalog, or if you go to the TVS diodes on Red Expert, and then you will have the appropriate TVS diode for 36 volts. This is very easy handle.
Perfect, great to hear that. Thank you very much.
Welcome.
So the next question is from Yannick. Can you explain the difference between reclamp and VBR a bit more in detail?
VBR is the voltage. If you exceed it, then the TVS diode starts conducting, means at this point it allows 1 milliamp current flowing through the TVS diode. The other one that you have got this VClamp max, is the value. That means if then the surge event goes bigger, that means this is the maximum voltage the TVS diode is capable to clamp. It cannot clamp to a higher value. Means if you have got, let's say, 500 volts, then the TVS diode will clamp at the maximum value of 48.4 volts at 25 degrees of 49.84 volts at 55 degrees. This is the maximum voltage the TVS diode is capable to clamp.
Thank you very much for making it clear what the difference is.
Yeah.
I think I got it now.
Okay, thank you.
So let's see. With a look at the time, I think we can do one more question. Is this one all right? Again to the TVS. How can I dampen high energy input transitions without overloading the TVS diode?
Depends on what is meant with high energy. Are we talking about 500 volts surge, 1000 volts, 1500, 2000 volts surge? Means what is the energy here? And this two-stage filter concept is pretty okay to clamp here more, because everything the TVS diode is not capable, the LC filter will manage it then at the later stage.
Perfect, thank you very much.
You're welcome.
So that's all we have time for today, but don't worry, all of your questions that are in the chat will be answered afterwards by Timur via email, so we will reach out to you. If you still have any questions left, feel free to still send them into the chat. We will check them later as well. Thank you very much for your attention, and I hope you enjoyed the session. I did. And thank you very much, Timur, for your time and the presentation.
Thank you. Always a pleasure.